Written test. Oh, look at this. I don't have to make up a test for you for a long, long time. That's good news for me. But you, what do you got? You got a programming test. But even that's after reading week. All right. So my understanding is you can hand in anything today and that gives you the marks, right? Isn't that the case? But still, you should know how to do the assignment so that you can do the programming test. And I certainly know I wouldn't want to be sitting on a terminal and having to write working code in whatever time they give us. It's not something that I would enjoy doing. Right? It means you have to memorize all this Java notation, which to me sounds horrific. Oh, we still got 1 minute. Yeah. So the what test?
Do you know the format? Are we gonna get like starter code or like blank and go? No clue.
No clue. No clue. My hope is that anything Jackie tells his class, he'll tell me to tell you. But he even told me not to tell you how long it was, which seems strange to me. I don't know. All I do know is that the purpose of the written tests is to test whether you did the assignments, right? The thinking, my understanding is that if you do the written programming tests, then you'll do fine on the written programming tests, right? You look blank like you don't know what I'm saying. Twice, but one, yeah. So there's programming. There's four things you have to do. You have to do programming hand in, and if you practice those, you'll do well at programming in the lab. That's what I was trying to say. And then there's the written theory and the exam theory. All right, we're starting now. So any thoughts about anything? All right. So if we go back here, we go here, we go here. All right, so if you kind of look through, what did we do last class? We did binary search, right? Both in an array and in a tree. And then we're going to do, right? I think these are all good things to do. All right. Oops. That's... All right. So who's viewing a block? All right. So this problem was given to me last time. I was co-teaching with James Elder, and he gave me this problem. And there are all these, the input is a bunch of buildings in a row. And what is it? I think you're standing, if I'm not mistaken, you're standing over here, and you want to see which buildings do you see? What is this? Let's get rid of it. All right. For each who's blocking its left view. All right. So, oh yeah, there we go. All right. So if you were standing in this building, right, who's blocking your view but this building, right? And if you're standing in the top of this building, right, then this building's blocking your view, right? Everybody kind of get the problem? And one of the reasons we're thinking about this is stacks are nice and loop invariants are nice and running time are nice. So all of these things come up in this example. All right, so running time. So this is saying for each building, you have to search back and to see who's the next one who's taller than you, right? So what's the running time of this going to be? We have n buildings. For each building, we're going to search back. No. No. Are you guys guessing? Right? Right? This guy is going to search there, and this guy's going to search there, and this guy's going to search there, and this guy's going to search there. N squared. All right? Right? We may have to search for n buildings, and for each building, you're going to have to search back, so that's n squared. Yeah.
Now I get it, 10 squared because we're comparing to the Burj Khalifa every time, and then the next building after that.
Yeah, for each building, it may take you order in work to find who's you're hitting, right? So, and clearly we want to do better than that, right? All right, so we want better time, we want a loop invariant, we want to use a stack. All right? So, oh, I made new slides. Which I might not have even told you about. Let's see what those new slides are. Okay, let's do these new slides first. All right, so out in the hall, people talk to me about what they're not understanding and not getting what a loop invariant is. And somebody, I think it was him, said, well, it's sort of, are we good so far, right? Yeah, that's kind of what a loop invariant says, is are we good so far? So it made me think, yeah, but what does that mean, good so far, right? And so a loop invariant is going to turn out to be our definition of good so far. And the slides I had here with the homeschool problem, I made something like 20 years ago, and they're new, new ways of thinking about it in my slides. So I've updated these, all right? So the problem is, we're at home and we need to get to school, right? So the precondition is I'm at home, post the condition at school, and so we can ask right? What is, I don't know what this set up professional audio settings. I wish it would go away. Go away, good. All right, so what is an algorithm, right? An algorithm has many inputs, but I'm narrowing it down to a computation. What is a computation? It's an algorithm on a specific input, right? So what is a computation? Well, somehow you travel a path from home to school, right? Given the input, this is what you do. And what do I mean by being somewhere on the screen? It's the state of the computer. And if you take 2001 from me about Turing machines and finite state automatas, what I really focus on is that what does it mean, the state of a computer? And so if you have code that's running, your state tells you what line of code you're on and the values of all your variables, right? You stop the computer in time and you say, what do I need to know so I can keep going, right? So if we're going to design an algorithm, then wherever you might be standing, you have to say, how do I take the best step towards school, right? And that becomes becomes his optimization problem, which is a little scary, right? So let's not try to get the best. Let's just a good enough step, right? And And so here from every state, what will the code in the loop do, right? We're going to have a loop and it's going to take some step. And I'm saying don't worry about the whole computation. All we want to do is, no matter where we are, we want to take a step that makes progress, right? Whatever that means. We're going to have some measure of progress that says, if I'm here based on my state, it gives me a number which says, how far am I from school, right? And in this picture, it can be just your Euclidean distance, right, that you measure with the ruler, right? So there's your kind of Euclidean distance of how far you are, right? And so the first, I don't think we've even done this kind of version of the slides, have we? We didn't, right? All right, so now you can ask the question, if at every point I take a step that gets me closer, am I guaranteed to get there? Right? Am I guaranteed to take a nice path there? No. Am I guaranteed to get there? Yes. All right? So just the other day, I made this red line, and I purposely made it so that for every circle, I moved a circle in, right? So I keep going. If I'm guaranteed that my distance keeps getting smaller, then eventually my distance will be 0, and I'll be there, right? Everybody see that? So that saves you from worrying too much about things, right? It's just, you'll get there if you keep making your measure of progress good. And in terms of running time, right, it's about keeping your initial distance small and making sure that you're making big steps, right? All right, so that was good. Now, well, this says, how do we know it works? And maybe this isn't a good slide because over here, we already know that it works, right? But I guess here the concern is, how do you know that the program doesn't crash, right? If you're going from home to school and you end up in a tree, then we don't give you instructions how to get out of the tree, right? So, right, this is what he was saying. Check to see, am I good so far? Am I on the path, right? So we're going to define what it means to be on the path, right? And, right, what defines this path, right? It's going to be an assertion or a loop invariant, right? So at any point in the code, right, any state that we might be in, we're at a particular point in the code, and that has an assertion. And the assertion tells us something about the state that the computer's in, right? And it says yes or no. I'm on the path, I'm not on the path, right? So that's what the assertion and loop invariant's doing. It defines which places are green, because those places you're on the path, right? And why do we want to do that? Well, first off, this isn't a unique algorithm, right? I could define a different algorithm which would have a different loop invariant, right? Insertion sort, selection sort, these are bubble sort, right? These are all sorting algorithms, but you're going to end up in different places along their paths. They have different paths, they have different loop invariants, right? So in some ways, to name the algorithm, what we're doing is we're naming what the path is. We're naming the algorithm, right? Now, sometimes instead of making a little narrow path, we make a really wide path, right? And what's the advantage of wide paths is then you can, your algorithm can wiggle and wobble a little bit more, right? You don't have to be so pinning down about what's actually going to be true as you go along this path. I mean, for example, we want the same path to work no matter what the input is. Here, I think I have different, right here. We could have different homes and different schools, and we want this one algorithm to work no matter what your input is, right? And so if the path is wide enough, then it can work for all of them, right? We want to say when you're at this line of the code, no matter what your input, no matter which loops you went around, if you're here, then it's true, right? And by having it broader, then we don't have to prove so much, right? It's a wider sort of net. So it can make the proof. Another reason for making it wider is you give, I'm the designer of the algorithm, but you might be the implementer, right? And it gives the implementer more flexibility. Like in selection sort, I say, grab some number from the left and put it where it belongs, right? But I haven't told you which number. And that makes for a much wider path, right? It makes the loop invariant. It just says there's some numbers on the over here that we don't know that are sorted, but I don't know which ones, right? That makes a wider path. And then as you go along the path, we'll get more and more numbers on the left, right? Does that make sense? So what's an algorithm? You define what the loop invariant is, the assertions, the path. You make sure that you know how to get from home onto the path, right? You make sure that you are able to define a step. And now the good thing, here's another reason having a loop invariant is good. You only have to define a step if you're on the path, right? If you're up the tree, then you don't have to worry about what the algorithm's going to do because we're assuming that you're not up the tree. And if you get up the tree, then the program's going to crash and we don't worry about it, right? So that's the advantage of this path is we're saying if you're on the path, then you have to say what step you're going to take. And what do we need then? That step keeps you on the path, right? And makes progress. And from the exit condition and the loop invariant, you need to get the post condition, right? Does that make sense? Do people follow these slides? Did they help any? Maybe you knew it already. Yeah.
That knowing that you're closer. Like yesterday, I was watching the AFC game between the Chiefs and the Bills.
Right.
I obviously like the Chiefs.
Right. Obviously.
So every time they got closer,
Right.
that was like an assertion.
Right.
Closer to getting to the touchdown.
It's more of a measure of progress. But yeah. All right. Everybody see the importance of loop invariant and measure of progress. All right.